Hello, welcome to Mr. Sweeney's AP Physics C class. In today's video, we're going to go through a drag force integration example. And this is going to mimic a actual problem that was on past AP Physics C exams. We're going to go through this example. And in this example, we have an object of mass m that is dropped from rest near Earth's surface, experiences a resistive force of magnitude kV. That means the resistive force is equal to kV, where v is the speed of the object and k is a constant. Starting from Newton's second law, we have an expression for the velocity as a function of time. So in this problem, I'm going to break down the points first. It's going to be 4 points. The first point is going to be for using Newton's second law to set ma equal to the gravitational force minus the resistive force. So it's using Newton's second law. That's the first point. Second point is for making it a differential equation. That's replacing the acceleration in the function you first write for dv dt. The third point will be for using a u substitution. And the fourth point would be for using a correct expression for velocity as a function of time, which is our ultimate goal here. So let's go through this step by step. So the first step we're going to do, we use Newton's second law in order to write an expression relating force and time. In this, we have net force is equal to mass times acceleration. And we also know that net force is going to be equal to whatever is unbalanced. And we have the force of gravity, which is mg, pointing us down towards Earth. And we have a resistive force of kV that is acting opposite our motion. So we could say that net force is also equal to mg minus kV. And then we set those two equal to each other, where mass times acceleration is equal to mg minus kv. This is where our first point on the problem comes from. In the second part, we're going to take this expression ma equals mg minus kv and make it a differential equation. A differential equation is just an equation that has a differential in there that would be two derivatives. So we take this acceleration function and we replace this acceleration term with dv dt. This is taking an f equals ma equation and turning it into a differential equation, saying that as velocity changes dynamically with time, these other variables will express how they do so. Now our ultimate goal, this is our second point on the problem, our ultimate goal in this problem is to get velocity as a function of time. In order to do that, we have to have all our velocity on one side of the equation, all our time on the other side of the equation. So we're going to do this first by separating our variables. In this next one, I've taken my dt and I've multiplied it by both sides. You can see my left-hand side of the equation now is mass times dv, and then our right-hand side is what that mg minus kv multiplied by dt. Taking it one step further, because in that last step I don't have all my velocities on one side and all my times on the other side, I'm going to further separate my variables by bringing all my velocity to the left and all my time in constants to the right. So I'll have dv divided by mg minus kv equals dt divided by m. And this is separation of variables. From this point, ultimately what we're going to want to do here is integrate this expression. Now the only problem here is that we do not have a usable law here for the integral of a variable that would be 1 divided by some constant minus this variable. So that's not an expression we have. So what we're going to have to do here is we're going to have to use a u substitution and replace mg minus kv with u, making it a little bit easier to integrate this. So mg minus kv will be u, but that only partially solves our problem on the left. It does simplify the denominator, which makes it easier for us to integrate, but now we're not in terms of v anymore, we're in terms of u. So we have to do something with this dv, and we're going to take this dv, and we're going to get the velocity dv in terms of du. So we could take the derivative of this u function and say du dv. The mg term becomes 0. The v obviously goes to 1. And we could say that du dv is equal to negative k. And following that, we could also say that dv then is equal to du divided by my negative k. And here we have a u substitution. The u is equal to mg minus kv. That'll replace the denominator on the left-hand side. And then our dv, which we now need in du, we have a replacement for dv because we know that dv is equal to du divided by negative k. So let's go ahead and make those changes in there. The first thing we're going to do is we're going to switch out the mg minus kv for u. So now it's going to be dv divided by u is equal to dt over m. And now we're going to replace the dv with the du, and that is du over negative k. I've pulled the negative 1 over negative k out because it is a constant, and in all our functions here, the constant will always pass through. So now this is 1 over negative k times du over u equals dt over m. Now this is some functions that we can properly integrate. So we're going to do that. We're going to integrate du over u, and we're going to integrate dt over m. And so taking the antiderivative, du over u is equal to ln u, and dt times t, or the integral of dt, just becomes t. So our function then just becomes 1 over negative k ln u is equal to t over m. Now I'm going to, since I have this in terms of u, going to replace this u with mg minus kv, and then we're going to start talking about our bounds of integration. So resubstituting in the u for mg, or resubstituting mg minus kv for the u gives us this function here, and now we're integrating over these bounds. On the left is from 0 to v, and on the right is from 0 to t, where that t is the velocity at that moment. So let's go ahead and integrate with those. So the left-hand term in here, we have ln of mg minus kv, that's the velocity aspect of it, minus ln mg, that would be mg minus k times 0, which is just mg. And then on the right, we have t over m for the t, minus 0 over m. Obviously, we're going to simplify this a little bit. We're going to get rid of the 0 over m because 0 divided by anything is 0. We're also going to move the 1 over negative k to the right-hand side because it is a constant, and allows us to isolate our natural logs on the left, and using our laws of natural logs, a natural log minus a natural log, the same as 1 natural log, numerator and denominator, we can come to a much simplified equation that says the natural log of mg minus kv over mg is equal to a negative kt over m. And here we're getting much closer to having velocity isolated on the left and time isolated on the right, so we can get one in the function of another. We do have to deal with this natural log, so we use the inverse function of the natural log, which is the exponential function. On the left, that makes the natural log go away. On the right, we have the exponential function raised to the negative kt over m. At this point, we're really close to having velocity isolated by itself. Our ultimate goal is to get that velocity by itself. So our next few steps are just going to be isolating v. We multiply both sides by mg, so we have mg minus kv equals mg e to the negative kt divided by m. Here we're going to further isolate v by adding kt to both sides and then subtracting mg minus, or e to the kt over m from both sides. And this really isolates our kv very extensively. And we have mg minus mg e to the negative kt over m equals kv. I'm going to factor out the mg on the left-hand side, so it's mg 1 minus e to the negative kt over m, and that's equal to kv. Divide both sides by k, and we are left with our function. Velocity is equal to mg over k multiplied by 1 minus e to the negative kt over m. Now in this problem, the first few steps actually went relatively quickly up through separation of variables. If you are doing this problem on an AP exam, if you have time, I would suggest solving it at full length. If you do not have time, you could always just start the problem, separate your variables, write your expression for Newton's second law, put your differential equation in there, maybe move on and then come back to it later on in the test if you have time.